the research that he has done. So with that, I don't take more of your time. From 2017 to the present, he has been working at financial institutions, a financial institution of Wells Fargo, and well, the time is yours. Thank you, BJ.
Thanks, Rogelio. Hey, walk me through. I'm trying to show my screen, right?
Yeah.
Click here to start sharing the screen, okay? Let me see, right? So what do I need to do here? Let me see. Switch screen to share. What you're sharing screen one? Can you see anything?
Yeah, we are seeing the Blue Jeans screen.
Okay.
So you just
hold on a second. Okay, can you see that now? My screen?
Yep.
My top?
Yep. Yes.
So you ready for
Perfect.
me?
Yep, we are ready.
All right. I don't know if people can see my face. You can see that I'm nothing like that picture that Rogelio just showed. I'm now an old man with a beard, not as old as Rogelio. He also has got a beard. Okay. All right.
I'm gonna close my video.
Yeah, please close mine too. Okay, thank you. Thank you to Rogelio and Graciela for inviting me. Can you hear me well, Rogelio?
Yes.
Okay. Occasionally I might lose some connections, but I think right now my internet is fine. So it's a pleasure to be part of this celebration, and thank you for inviting me. I'm going to be talking about machine learning. It's really very basic ideas here. So it's really an introduction to the ideas of machine learning and its relationship to statistics. And it's really we have an overview tutorial, Rogelio, and I'll send it to you. You can circulate to the students. It's a paper, okay? And okay, so I'm talking about work I've been doing for the last 4 years or so in the bank, Wells Fargo Bank, and I will try to give some context, and I'll use some applications to illustrate the ideas. So here is the outline. I'm going to be talking about some introduction to machine learning and what people call AI. And I'm going to be focusing on what I call data-centric machine learning. Machine learning has been used also to solve very complex partial differential equations, for example, deep learning. I'm not going to be focusing on that. I'm going to be talking about machine learning in the context of prediction in particular, and where it is useful and how it contrasts with statistical models. So in particular, I'm going to be focusing on what people call supervised learning or prediction, or regression and classification problems, okay? And I'll give you some background on what the term I use is modern supervised machine learning. And then we'll talk about some examples, and I'll hope to finish in about 40 minutes, so we have some time for questions. So here is something in the way of background. The term machine learning was first used by Arthur Samuel. He was at IBM at that time in 1959. And the original definition, so to speak, which is what you'll see if you Google it, it says gives computers the ability to learn without being explicitly programmed. Of course, that is rather vague. What does that really mean? And of course, machines themselves don't learn, right? It is just the algorithms that have the capability to adapt and learn from the data and make predictions and how they change over time, right? Ability to adapt over time. Perhaps a better description is to say machine learning is the study and construction of algorithms that can learn from data, right? Summarize features, recognize patterns, predictions, and even take actions, okay? And that's probably a more descriptive explanation. It is related to statistics, and I'll try to be a little bit explicit about that, particularly the area of what we call computational statistics. But the approach, the framework, or the paradigms underlying statistics and machine learning are quite different. Now, artificial intelligence is another term that has become very popular. And there are a lot of people who confuse machine learning and artificial intelligence, and they use it interchangeably. Artificial intelligence is a much broader concept. It is related to making computers behave like humans, okay? And I'll talk a little bit more about that, right? Now, machine learning is strictly a subset of AI. It's one of the pathways, one of the ways to accomplish goals of an AI project. Now, the term the background to artificial intelligence has a long history. Is intelligence, and how do humans think, how do people do reasoning in philosophy, logic, and so on for a long, long time, well before the term artificial intelligence was coined. And this was coined by John McCarthy at MIT in 1956. It turns out there was a big symposium at Dartmouth by a number of well-known people in computer science that included John McCarthy, Arthur Samuel, and a number of others at Dartmouth, and that's where a lot of these ideas started. At least things like even neural networks and so on. Although neural networks, I should say, have been around a bit longer. Okay, so what is artificial intelligence, right? It's very, very difficult to define it, right? So you can think about it as a study of artificial intelligent agents, whatever those terms mean, right? So these are devices that perceive and understand the environment, collect data about the environment, and take actions that maximize the chance of success at some goal, right? That's, again, a very, very broad term, right? There are really good examples of that. Perhaps the most well-known example of artificial intelligence right now is what is called autonomous driving, right? Autonomous driving. It's a very good example where lots and lots of different things are going on. You get lots of different models about how people drive and how people make decisions based on all of the information in front of them. It's got a lot of sensors in a car, collect sensor data, and based on historical modeling and various kinds of intelligence, an autonomous driving car makes decisions, right? That's really a good example, right? AI techniques, they have been around, as I said, well before 1956. And people say that these techniques have gone up and down. They use the term AI winters. AI winters means that there were times in which the technique wasn't very used, and people thought it wouldn't work. And this happened when the earliest version of neural networks, called single-layer perceptrons, were invented, or discovered, I should say. And people said, well, this is not going to, cannot solve some simple problems. And and people for some time got excited, and then sometime they said, no, it cannot work. But what has happened in the last 20 years or so, right? It's a lot of excitement. And why is that? There's tremendous advances in computing power, we all know, right? We all know that. And then there is computing and data architecture. They have the ability to collect lots of data, right? Advantages in sensors, data collecting sensors, availability to store data, ability to move data, and ability to compute and do all kinds of very complex calculations incredibly fast, right? So all of this means that very complicated techniques that were not possible to implement unless you have access to supercomputers now can be done on your laptops, right? And so a lot of these techniques, a lot of these developments and advances have made possible incredible development of techniques, not just in computer science and statistics and neural networks, but also in computational platforms like TensorFlows and PyTorch and all of that stuff, right? And a lot of these advances are not necessarily being made in universities. Some of them are, but a lot of them are being made at Google, Microsoft, Facebook, and Amazon. So these are the people who are at the cutting edge of a lot of this work in artificial intelligence. And we've heard about deep learning neural networks. I would mention some of them. And these neural networks have become the core, the bread and butter of artificial intelligence, particularly in image analysis and pattern recognition, right? And I've listed some of these examples here: pattern recognition, autonomous systems like drones and self-driving cars and all that, right? Okay. I'm going to focus myself on what we call machine learning. And I have broken this up into several different tasks, learning tasks, right? And I'm going to be focusing on what's in the black box here, supervised learning. And we'll talk about that, what supervised learning means. But there's also unsupervised learning, semi-supervised learning, reinforcement learning, and lots of other names are coming up, representation learning, transfer learning, and so on and so on. That is not the purpose of my presentation. My presentations talk about supervised learning. I'll briefly touch on unsupervised and then get into details about supervised learning. Okay? What is supervised learning? And all of us in statistics have known this for years. It's just a new name, an old wine in a new bottle. The problems are regression problems and classification problems. Those are the most important classes of problems, right? Regression and classification, these have been around for a long time. And as you know, regression was originally developed by Galton in the late 1880s and 1890s. So what do we have in this setup? We have some data, X's, we call that covariates, independent variables, predictors, whatever, and responses, yi. And what we want to do is understand the relationship between X and Y. Okay, that's really what it is. And we call Y's as responses and are labels, and they're available for a set of data. X's are predictors, right? And our goal is to understand the relationship between X and Y. And Y can be a classification problem, good, bad, yes, no kind of thing. Or it could be a continuous regression problem, right? And our goal is to understand, not only do prediction, but understand the relationship. Okay, that's really what regression problems are, or more fancy in computer science, they are outlier detection, principal components analysis, cluster analysis. Things that we've been doing for a long time are also examples of unsupervised learning. And what is the problem here? The problem here is that we just have these X's. There are no labels, no Y's. So we have these X's, there are no labels, and these can be very high dimensional, like 10, 20, 2000. This could be, as Mark Genton was talking about, they could be just multivariate data, they could be functions, they could be images, and so on. And what we want to know some underlying pattern in the data. For example, if you look at these things, at this plot here, scatter plot, you see plots of data, and you can see there's clusters, right? So we want to know, are there clusters in this data? Is there any kind of underlying lower dimensional representation, or is there, are these p-dimensional data lying on some lower dimensional manifolds, whether it's a linear space or nonlinear space? For example, this could be x1 and x2, and the function could be, it could be lying on a circle, for example, or a sphere in high dimensions, and we want to understand that lower dimensional representation. And I'm not going to get into that. There are also machine learning techniques for that now. I'm going to talk about now, and if you look at unsupervised learning, the traditional techniques that we have used are box plots and for outliers, Mahalanobis distance, convex peeling, multivariate depth, and Mark Genton talked about some of these, notion of distance for multivariate and functional data. And here are some other techniques that I'm going to let you read. I'm not going to get into that. And, so I'm just going to show you some examples of algorithms for unsupervised learning, both old and new, right? And what I've put in new, things like autoencoders. These are nonlinear versions of principal components analysis, right? So we know about PCA, but autoencoders do nonlinear dimension reduction. And we have seen that in what people call manifold learning as well in the old days. Not old days, in the 1990s and 2000 and so on. Okay, I'm going to skip semi-supervised learning and also reinforcement learning. I have these slides are available from Rogelio, and so you can get them if you want them. And I'll also forward that paper I'm talking about. So I'm going to be focusing on supervised learning. And what do we do? What do we know in what I call traditional statistics? So let me review that quickly. In traditional statistics, again, we have the data, we have the predictors, and we have the labels. And what we are interested in is, and let's suppose there is a input-output relationship of this kind. The y is some function of the x's plus some error, right? What is our goal? And remember, this is not always the case. We can have binary data here, we can have count data here, and so on. But what is our goal? We have two different goals here. The goal is to figure out what f is, right? We want to get an approximation or a representation for f. And once we have that f, we want to do a number of things, and there are two main things. We want to predict. We want to predict. I give you a new x, I want you give me y hat, right? Y star. If I get x star, I give an x star, you f hat to give me a y star. That is a prediction. What is going to happen outside of the sample I've observed, whether it is over time for other people or what have you. The other thing that traditionally we have done in statistics is to understand f hat, the input-output relationship, right, between x and y. Which of the x's are important, right? And is the relationship linear? Is it nonlinear, right? And we want to do variable selection. We want to understand if I change x1 a little bit, what happens to y? We call it sensitivity analysis and all of that stuff, right? That's what we've done for years. The oldest technique around is the parametric models, right? We assume f is some parametric function, which g is known, and there are some unknown parameters. And we want to be able to estimate, g is known, so it's just a matter of estimating beta. And the simple linear models, linear regression, logistic regression, Poisson regression are all part of this, and they're all called generalized linear models, right? And then we have more complex models where I say, the model is beta 1 not times x1, beta 1 times some complicated function of that, and we call that additive linear models. We have nonlinear models, and so there are a whole bunch of techniques we have. We have splines, we have GAM and all kinds of techniques that we have developed over the years. Fitting methods, OLS, weighted least squares, maximum likelihood estimation, and then a lot of techniques for model selection, diagnostics, and inference, right? This is an area that has been in development for a long time, and a lot of new ideas in the last 30, 40, 50 years. People like Bryman and Friedman and Mars and all of that stuff, right? Multivariate adaptive regression splines. Now there is another area that came about after the path-breaking work of Charles Stein, and also what is called ridge regression by Hull and Kennard. That was 50 years ago, by the way. There is a special issue in Technometrics on ridge regression. Please take a look at it. There is a paper by Trevor Hasty there, which I organized. And the idea here is to not only minimize the sum of squared error or whatever we're doing, but penalize it so that we are not overfitting, right? And the penalty depends on whether it's a L2 penalty, L1, or whatever. That's really what ridge regression is. And there are a whole bunch of other techniques that I mentioned: kernel regression, nearest neighbor, local smoothing, splines, and all of that stuff, right? That's a rich area. Okay, what is machine learning in this space, right? So the computer scientists are very generous, right? What they say is, well, everything that you guys in statistics did, we will call it machine learning. Okay, so they're very generous. They have taken everything that we said and they're calling it machine learning. Okay, so least squares has become machine learning. Logistic regression has become machine learning, right? In my work, in our work, we separate them. Okay, we separate them. So all of the things that we know, I would call that statistical algorithms. This distinction, of course, is blurring. Some people are not very strict about this. And when I talk about machine learning in this presentation, we talk about things like support vector machines and ensemble methods, bagging and boosting, and neural networks. Okay. So I'm going to be talking about bagging and boosting and boosting and neural networks today, okay? And all of these things, like even CART has been around, and bagging and boosting just build on CART, right? Classification regression trees, okay? All right. Let me start off with ensemble algorithms. And here is the basic idea of what people call ensemble. Ensemble, is just instead of doing something just once, you do many different things and you combine them. So that's really the idea here, right? What do? We so far in regression and everything, we have a set of data S, and we could either take all the data or we could split it into training data and test data. We can do cross-validation or whatever. So we have a set of training data from the S, and then we fit a model. We fit a model to L, right, to the training data. And this could be a logistic regression. This could be a classification and whatever, right? And then I look at the model. I do all kinds of testing diagnostics, and I'm happy, and I refine it, and I'm happy with the model. And then I use it for other purposes, right? For prediction, you give me a new X star, I can use F hat to give a Y star. And usually in a linear regression case, F hat is a set of equations, explicit equations. But in more complicated cases, for example, in multivariate adaptive regression splines, Mars, the equation is very complicated. And so, you can think about it as an implicit function. What happens in ensemble algorithm is different. You have a set of data, and what you do is that you take different sets of data from the original data S. So let's suppose I take a subset, I fit a model. I take another subset, I fit another model. I take another subset, I fit a model. And these subsets don't have to come from the original data set. They can be results of this fitting here that you'll see. So what do? You have K different models, okay, at the end of the day, and you combine them. What you do is that you take these K different predictions and you combine them to get an overall prediction, right? That's what is called an ensemble algorithm, okay? And so at the end of the day, now given that H is not an explicit analytical function. It's a function. You give it an input, and the software, your algorithm, like a model, object, and R, can evaluate that function and give you a Y star, right? So this H function, or H hat, or whatever you want to call it, is it's a very complicated function. Okay, and we'll see examples of that, right? So, but it turns out it has very good predictive performance. Okay, so the idea here, as I'm showing you, is improving performance by combining the output of several individual predictors, one way or the other. And there are two main techniques: bagging, which is an idea due to Efron, and boosting, which is an idea to some people who used to be my colleagues at Bell Labs, but they are not there anymore. One of them is at Princeton, and the other guy is at UC San Diego now, okay? And there are a number of other ideas: model averaging, majority voting, ensemble stacking, that people also use. All right, so let me just show you two quick examples of this, right? So random forest, many of you now have heard of random forest, popularized by Bryman, and Cutler was his PhD student. And she used to be at Utah State. I don't know where she is now. But the idea is that, let me just use the tree, this picture to tell you the ideas, right? You have an original data set. You take a sample. You take a bootstrap sample of this, okay, a bootstrap sample of this, and then you grow a tree, okay? You grow a tree, regression tree, okay? And then you take another bootstrap sample, you grow another regression tree, and you keep on doing it, K bootstraps, and then you take an average. You take a simple average of all the predictors from the bootstrap tree, right? And remember, what does a bootstrap tree give you? It is a piecewise constant. What does a regression tree give you? It's a piecewise constant model, right? You split the observations into some regions, and each leaf node of the tree, you fit a constant model. So it's a piecewise constant model. So this is an average of many, many, many piecewise constant model. And you can have as many as 100, 200, 300 trees, okay? And that's really the idea here, right? So remember, looking at averages of 100 or 200 trees and looking at the prediction is very, very difficult to interpret, right? Even a single tree it can be unstable, can be hard, but many trees is very difficult. The idea here is that you do random bootstrapping of rows, and Bryman actually said you can also randomly subselect the columns or the X's, and the trees, because they're bootstrap, are independent. And you build deep trees. And the issue with deep trees is that the bias is small because you're going down a lot, so you're trying to capture all the structure. But it turns out the trees are unstable, especially if they're correlated. They would be very, very unstable. So you average them. When you average the trees, you reduce the variability and reduce the instability and avoid overfitting. Okay, that was Bryman's big idea, right? And so that is an example of bagging. And there are what we call tuning parameters that we choose, number of trees, tree depth, and so on. Now, boosting is another instance of ensemble method, okay? And it's quite a different idea. It was originally done by Shapiro, who was at Bell Labs, and then Freund and Shapiro came up with an AdaBoost algorithm for classification problems, binary regression problems. And Bryman, in 1988, showed that boosting can be thought of as an optimization algorithm. It's actually a gradient descent algorithm, right? What boosting does, and I'm going to tell you what that is. And then Friedman, in 2000, used Bryman's idea, Jerry Friedman at Stanford, used it and said, hey, if that is really an optimized algorithm, I don't have to use AdaBoost or what they did. I'm going to come up with a very general gradient boosting algorithm. And he came up with the name GBM, gradient boosting machines, right? And gradient boosting is just gradient descent plus the idea of boosting, okay? And what is that? What is the idea of boosting? So what do? You take your original set of data, Y's and the predictors, and you fit an overall model, right? You fit an overall mean model, for example, okay? You just take the overall mean from this data, right? Like we have, ignore the predictors and just fit the overall mean. And then now you go to the next step. You take these Y's, you subtract of the means, take the Y, subtract of the means, and you have the residuals. And you fit another set of, in this, again, you see that you fit another tree, right? You fit a tree, a small, and they call it a stump or a short tree. You don't fit long trees in boosting. So you fit a tree, and to get another set of predictors, and then you subtract this fit again from the east to get another set of residuals, and then you take this again, and then you fit another short tree. You keep on fitting new models to these residuals, right? And the idea here is the residuals, when they are big, they're not good, and I want to really pay more attention to regions where the fit is not good, okay? And this was the big idea with Shapiro and Freund and Shapiro came up with, which is called boosting. Boosting means you look at the ideas where the fit is not good, you weight them more, and then you fit them, and then so that your new fitted model pays a little bit more attention to the space where the model is not good. So you keep on doing this, and then there is some stopping rule, at which point your final model is your original mean model plus all of these weighted average of all these models that are fitted to the residue. Okay, and this is what you call a hyperparameter that need to be optimized, and even how many trees, how many boosting steps, and there are a whole bunch of hyperparameters here. This is the idea behind boosting, and it turns out this idea can be thought of as taking think about these trees as an initial step, an initial guess into the model, and then you keep on improving upon the model, right? And that's really what Friedman showed, okay? And the trees here are short because you don't want tall trees. You really want, the whole idea here in boosting is to reduce bias, okay? So that's really, you don't need big tree as opposed to random forest. So neural networks is a more complicated concept. Let me be very quick here. The idea here is to mimic biological neural networks, how your brain works. And so those of you know a little bit about how the brain works, and the idea here is that you have different neurons surrounding a particular, different kind of neurons that are giving input to another neuron. And depending on the impulse, if the sum of these impulses are high enough, this neuron fires. And so this neuron fires means that some action happens. Sort of a very overly simplistic description. And neural networks are supposed to do this. You're supposed to mimic this as a computational algorithm. You have a bunch of inputs. All these inputs are giving, and you have a bunch of hidden layer with a lot of neurons. That's how many neurons is a hyperparameter. And you have all of these inputs are aggregated in some way, and then if they exceed a threshold, they fire. And how do they exceed a threshold? There are what's called activation functions, and all of these results are then combined and into a final output. I know I'm going too fast here, but there is a lot of stuff that can be said about neural networks, and I'm not going to do enough justice. So I'm just going to go through this very fast. The number of hidden layers could be 2 or 3. There are many hidden layers here. It's called a deep network. This is a single layer network, and the number of nodes here is a hyperparameter. And how do you optimize these things? The so-called weights here. And the idea was to do what's called backpropagation, which is an idea that was popularized in the 1980s. So many ideas here, and I'm just don't have the time to get into that. Okay. All right. And there's something called hyperparameter optimization, and I'm going to skip that slide as well. And let me start getting into examples, okay? Just so that I can give you a feel for how these things do. So the example one is mortgage data. Now, many of your students, you probably don't have mortgages. I don't really know how the mortgage structure in Mexico works. In the US, if you want to buy, it doesn't work. If you want to buy a house, for example, you have to pay some down payment. You go to the bank or some financing institution, you get a loan, and that's called mortgage. And what we really want to, as a bank, when it gives loans, you want to be able to track the loans and see how many people are paying all the monthly payments, how many people are defaulting, means they have stopped paying the payment. How many people are paying off the loan too early, because if people pay off the loan too early, we also lose money, right? So that's the kind of things. So, and this is something called prime real estate. What that really means, real estate related to some what we call prime portfolio, very high, low level, low risk, or very prime property, I should say. That's really what it is. So the data set is 7 million accounts. We had 54 predictors. Response is binary, whether the loan is in trouble or not. In trouble catches a lot of different categories. For your purposes, you can think about it as somebody didn't pay the loan for 6 continuous months, which means that loan is in default. That's how the way we define it usually. So a whole bunch of techniques can be. So what we want to do is that we want to model the probability of default, the probability that somebody will default given these 54 predictors over a period of time, right? We have data for these people over 30 months, 30 years, 50 years, 15 years, or whatever, 12 years, 10 years data, right? We look at all of the historical data of, a subset. We typically have billions of accounts, so I'm just showing you several millions. And I'm going to show you how 3 different techniques compare, right? Logistic regression, gradient boosting, GBM, and random forest, okay? And remember, this is a binary response. So the logistic regression is the simplest possible model. What we did was we took these 54 predictors, we did some variable selection, and and then we did some transformation. So we selected a subset of the variables, and we used what's called time varying predictors. So it's a fairly complicated logistic regression model. It wasn't a simple model. So some of you may be familiar with what's called ROC curves, okay? So this says at different false positive rates, what is the true positive rate? You fix false positive against true positive. And what you really want this curve to do is that you want the curve to jump up to jump up to 1 as quickly as possible and be remain at 1. That's the best possible response. But you can see that doesn't happen. It goes up to 1 slowly. So if you entertain a lot of high false positives, of course, you can get a lot of true positive rates, right? So you can see the red line is the logistic regression, and blue and I'm sorry, the blue and red and green lines are the ensemble machine learning algorithms, and the higher the better, right? And one way to summarize these curves is through what is area under the curve. You look at the area under the curve, and for logistic regression is something like 0.8. For random forest is 0.852. For gradient boosting is 0.865. So there is about a 9 to 10% what we call increase in predictive performance, and in our business call it a lift in predictive performance, right? So it's better. And so you can see that in this particular case, machine learning algorithms do better in predictive performance. And that is indeed the case in lots and lots of examples that we have tried and other people tried, right? Even well-trained logistic parametric models do not do as well as logistic regression, random forest and GBM. And the nice thing about these guys is that you don't have to do very complicated feature engineering and variable selection. Okay, this is a little bit better than what we've seen, but sometimes it's not as big as a lift as this. Okay, here is a second example. This is time series data, confidential data. I cannot get into exactly what it says, but it's a data on patterns of people depositing, taking out money, and how much money they deposit when, and how much money they take out, what kind of different accounts they have, savings account and checking account and so on. So there were a whole bunch of variables, and it took us about 2 months talking to experts to handcraft these predictors. And then we developed a good classification algorithm, logistic regression, gradient boosting, random forest, and also something called a convolutional neural network, which I'll talk about in the next slide. So what we did was, from the 75 variables, we did variable selection, took the top 10 variables, interactions, and look at the amount of time it took us. It took us about 3 months to get to this stage. And we fitted a lasso logistic regression. And this is the prediction accuracy. And the accuracy, so what you're seeing here is a cross-validation. What we did was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we withheld 10% of the data. We trained the model on the 90%, and then we predicted on the remaining 10%. We held out, and we did this 10 times, and the average performance, all that, is 0.97, right? So that's a pretty good model, 0.97. So now let's take a look at what GBM and random forest do. GBM and random forest, here is logistic regression, is GBM and random forest. This scale is misleading because it starts off at 0.96 or whatever, 9, I can't see it, I'm too blind. Okay, but you can see there is a little bit of a lift. So it goes from 0.968 to 0.985 and to 0.987, right? So there is an improvement in using logistic regression and random GBM. Now here is the neural network, which is the blue line. And the nice thing about neural network is we didn't have to look at the 75 variables, which we handcrafted from the original time series data. You can just throw in the original time series data, right? And this is what people do in pattern recognition. So you can think about images, right? In image analysis, people don't do any kind of handcrafted predictors trying to get some X and Y. They just throw the original image and then use neural networks to understand the pattern recognition. And that's what we did. And we didn't really tune that. And you can see the convolutional neural network still, without a lot of manual work, does really pretty well, right? And that's really the power of neural networks. That in data like time series and image analysis, you don't have to do feature engineering. You don't have to do variable selection. You don't have to do handcrafted engineering or use subject matter expertise to identify those variables. Okay. Now, Let me just very quickly go through something about machine learning models, right? So what have I done so far? I have talked about machine learning models, three different kinds of commonly used machine learning algorithms: random forest, gradient boosting, and there are different implementations of gradient boosting. Probably the most common one right now is called something called XGBoost. And there is a whole story about algorithms and open source algorithm, and Python and scikit-learn and all of that stuff, right? Which I'm not going to get into. Now, the problem, as I told you, is that with logistic regression models, with 10 variables, even with interactions, I can interpret the model. I can interpret what is the input-output relationship because there are coefficients, right? I can interpret them. But these GBM and random forests, I give an X, it gives me a Y, but I don't know the F hat. What exactly does it do? It's a black box, right? That's what people say. It's a black box. We need to open up the black box, right? And that's the biggest challenge, okay? The predictor is only implicitly defined, and we don't really know what is happening inside and how to understand what's happening inside, right? For example, if you want to use the machine learning to drive a car, and then somebody has an accident and the person dies, you want to know what happened. What went wrong, right? It's not easy to pick under the hood of a machine learning model. Similarly, if you're doing brain surgery, right, you're not going to trust a black box model without knowing how the black box model operates, right? So this is one of the hottest areas of research right now, okay? Now, the people who developed some of these algorithms, like Jerry Friedman, have come up with some very early ideas to look at one-dimensional summaries, two-dimensional summaries, and things of that nature. But a lot of these ideas are just very, what I would say, very elementary, very basic. And if you want to know if the model is behaving in some high-dimensional space, and is there some complexity going on, some very high-dimensional interactions, it's very, very hard to tell what's going on. And that's really one of the problems with machine learning. If you're interested in just prediction, and there are a lot of problems where you're just interested in prediction, right? Like recommender systems. And you know that in Netflix, there was a big Netflix competition about 10 years ago, and people came up with models that improved on the prediction by 0.00001% or something, and they got $1 million, right? And there are a lot of Kaggle competitions that you probably have seen, you've been participated. Same thing. You take the variables X and you take X1, X2, you take the ratios, the sums, the differences, and you square them, whatever, and you throw them in just so that there is some information that improves them. People don't care about the underlying model. Multicollinearity, the presence of correlation, doesn't hurt you in prediction. But if you want to understand what's going on, which is a lot of applications, like in banks, when we make decisions, when we give somebody a loan, or when we don't give somebody a loan, we have to explain why. We got to tell them by law, we have to say, why didn't this person get a loan? It's very, very important. And so explaining a model is very important. And so that's why people haven't completely converted to machine learning models, and we are still using them in an experimental framework. Okay, and so I've talked about what do you want to know? What are the main drivers in the model? If I have two highly correlated variables, which one is really interpretation? Can I do any kind of causal inference? All of that stuff, right? And there are a whole bunch of tools here, local importance, global importance, PDPs, partial dependence plots due to Jerry Friedman, two-dimensional PDPs, H statistics. A lot of these things have come up. And now there are local interpretable models that is called LIME, locally interpretable model agnostic explanation. SLIM is a paper that we just have come up with. SHAP is a technique due to, the original interpretation was from Shapley. He's a game theory guy from UCLA. And we have written a bunch of papers on that, and it's a very hot area for research in computer science, as well as in Google and so on, right? A lot of people are working on it, and I think in the presence of, correlated data, very few of these techniques work well. So I think it's a ripe area for research. I'm not going to get into any of these examples. I don't have time. There are things, for example, something called variable importance, and you can use to do these plots, bar plots to say, hey, the most important variable here is loan to value, right? FICO score is some kind of a credit scoring, your basic credit score, right? These are the important variables. And here is a comparison of XGBoost and random forest, right? So there are different techniques out there. I can't do justice. This is showing you the input-output relationship. For example, this shows you that input-output relationship is the one-dimensional input-output in relationship between the loan-to-value ratio versus your predicted probability of default. You can see it's flat, and then it increases, and and it reaches some value here. So the whole thing here is that it's nonlinear, right? And the nice thing about these algorithms, you don't have to try to figure out what this input-output relationship is upfront. The algorithm does it for you and gives you the relationship. And this relationship includes any effect on interactions as well. Now, it's just not the main effect. It also includes the results of interactions. You can see some funky behavior here, and that's because there is not enough data, and because of that. So typically, you would apply a smoother to this to understand the real relation. Okay, I'm going to jump through all this, and let me just do some summaries. Machine learning models are well suited for large data sets, right? And really the gain in predictive performance is N, the number of observations is large, at least in the hundreds of thousands, and really P is very large, right? Hundreds. It's a semi-automated, I say semi, it's not totally automated. It's an automated approach to feature engineering, identifying what transformation to use. You don't have to worry about interaction, it takes care of it. You don't have to worry about variable selection, right? A lot of open source algorithms, and so on and so on. Generally very good predictive performance, right? But the model interpretability is the big challenge. And let me just finish and with about 5 minutes left. Now, there is a very nice paper by Leo Breiman that some of you have already read, I hope, called Statistical Modeling, the Two Cultures. So this is a good paper because it talks about the view of the computer scientists, so to speak, or the algorithmers, and the old view taken by us as statisticians, right? So, and it was a controversial paper. He gave, if you go through, look at this and look at the discussions of these by people like David Koss and Brad Efron and others. He took an extreme view, and I think he was purposely trying to be controversial. We basically said life is all about prediction. He said most of what we do is prediction, and we don't really worry about model interpretation. I mean, he took that extreme view, right? So to speak. But the point here is this, right? In statistics, what do? The goal is understanding the model, right? We have some data, and we believe the data were generated according to some data generation mechanism, and we want to understand the data generation mechanism, right? We want to understand the key drivers. We want to estimate the parameters, look at uncertainty, testing, confidence intervals. We do a lot of model diagnostics and so on. So our whole thing is interpreting model, right? But in algorithmic model, the goal is best predictive performance. I have a set of data, and the way I do validation is that calibrate is that I break it up into randomly into test data on training data. And on the training data, I fit the model and see how it performs on the test data so that there is not overfitting. No intrinsic interest in the data generation process. Life is all about prediction, right? So these are the two different worlds in which people have been operating, right? And but the reality is that there are large classes of problems where it's just prediction, but there are also large classes of problems where there's understanding the model is important. So the key challenge here is to exploit the power of machine learning in order to improve our predictive performance, yet also do models, model interpretability. That, I think, is a very, very exciting area. All right, I'll stop there, Rogelio, and that's it from me. And I'll be happy to answer. I'll take a few questions.
Thank you very much. So you think that you take the view that we have to compromise. I mean, we don't have to go to the extremes, but taking the best of both worlds. And but I also Yeah, I agree with you.
Well, it depends on the context, right? If you want to just do prediction, you want to predict the elections, for example, and nobody in the U.S. has done a good job, but suppose you want to predict the elections, you don't really need an interpretable model, right? But if your model goes wrong, doesn't do a good job, you want to dig deeper, right? So there are some problems are legitimate religious, which is fine, okay? And and they do well on historical data, you're good, right? That's what I'm saying, right? But if you want to do interpretation, you may have to sacrifice some predictive performance. That's my take on life. That's our experience.
But still, Professor Cox in the morning, I think that he implied that yes, it's not 100% kosher to just have a method, an algorithm that performs well on a bunch of benchmark data, and say you kind of have a universal tool. And so he was kind of saying, no, that's not the way. On the other hand, Professor Peña just mentioned that remind us that AIC AIC is really based on giving a premium on predictive performance. So yeah, so all these in all these talks, I have the feeling that yes, we have to compromise and have a common sense on what is the problem at hand.
Yeah, I think like everything else, the answer is it depends. The answer says it depends. It depends on your goal. What is the problem, right? You're not going to come with a single tool to the same tool to different problems, right? Yeah. But I would say that we statisticians have been dishonest in the past. We claim that we know the underlying data generation mechanism, but in the way we do, we claim that we have looked at parsimony, we want to interpret the model and so on, right? But but we far too long been happy with fitting very simple models to data that haven't really fit the purpose ahead. Because, for example, in banking, what is it that we need to do? And none of these models, none of the historical models are going to fit data that changes over time. In banking, we are interested in predicting what's going to happen in 2020, 2021, 2022. Now, all of our historical models have not done a good job with COVID. With COVID-19, all the models are bad, right? And there is no way you're going to be able to use historical models to predict a future when the future is not going to be representative of the past, right? That's number one. Number two, we are talking about prediction based on observational data. The
broadcast of Facebook Live has stopped.
Yeah. So if you want to do causal inference, right? If you want to understand what is the real thing going on, it's very, very hard to base it on economic data. You need to, if it is okay, if it is an underlying
Esta reunión está siendo transmitida en Facebook Live.
Physics-based model, then it's okay, right? If you know underlying thing, and you're approximating by a model, right? Statistical model. But if you don't really know, it's very hard to do causal inference in any of this and try to pretend that we really know the truth, right? I know I'm over time, so I should probably stop.
Well, again, thank you very much, Dr. Vijay Nair, and well, we are very, very grateful to count you as a friend. Thank you.
It's my pleasure, and all the best for the rest of the afternoon. All right,
Thank you very much.
Okay.
You're welcome. Take me out, please.
Thanks.
Héctor dice que lo saques tú. Gracias.
¿Puedo empezar? Okay.
Adelante, adelante, adelante.
Okay. It is an honor for me to introduce our next speaker. And of course, he's a friend of CIMAT, Professor Balakrishnan, or Bala as he likes to be called. He's a distinguished university professor at the Department of Mathematics and Statistics at McMaster University. He has visited CIMAT several times, one at CIMAT Monterrey, yes. A bit of his trajectory is he has been elected as a fellow of the Institute of Mathematical Statistics, is a member of the American Statistical Association, the Institute of Mathematical Statistics, of course, and some more. So, talk about his academic production will take a long time, because he has worked on different areas. So, I will try to summarize it as follows. I hope that doesn't sound ambitious, huh? But I am quite sure that each of you knows some of his books or papers. So it speaks for itself. So Professor Bala, welcome and share your conference with us.
Thank you. Can I share
Besides,
the
he
screen?
knows how to cook very well.
Okay.
Okay. Is the screen visible?
Not yet.
It says it's being shared. Is it visible?
No, choose
Not
the
yet.
Acrobat Reader in your Blue Jeans.
Oh, it says you are sharing Blue Jeans. Are you sure?
No, but you should share the Acrobat Reader part. Share the
Share
application
the Acrobat Reader.
Yeah.
I did yesterday. Just a second. Acrobat Reader?
Yes.
That's perfect.
Okay, that's good.
Is it working? Okay. Can everybody hear me?
Yes.
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 Let me first start by thanking Graciela and the organizers for inviting me, and also for regarding me as a friend of CIMAT. I have visited many times, both in Guanajuato and also in Monterrey. I always enjoyed my trips for, like David Cox mentioned, for academic reasons, as well as for the kind of hospitality that I receive. So I fondly remember my visits. For those of you who are curious about the US election, nothing is known yet. So I have a feeling that until CIMAT organizes 41st anniversary, we may not know the result. It looks like. So,
hopefully not.
it looks like that. Okay. I'm going to talk about a topic.
Hey, Bala, all of you foreigners should stop talking about U.S. elections, okay? You guys are meddling in the U.S. elections.
We share border, unfortunately. I'm going to talk about a topic that I have started working on recently. It is based on a few research papers that I have co-authored with some of my students that are to appear. And the topics that I'm going to talk about have been touched upon by many of the speakers before, in particular about the talk that Vijay just gave, in particular on model selection or variable selection, etc. And I'm going to concentrate on dimension reduction and variable selection, but I want to consider a high-dimensional multivariate linear regression setup. And I'm going to talk about some specific techniques. This is a technical talk, but I try to minimize as much of the technical details as possible. I will highlight the results, present some simulational results to justify the theoretical results shown, and also give you some practical data sets where we have used these techniques. This is, like I mentioned before, it is co-authored with a few of my doctoral students, and one of them has graduated already, and the other two are still in the process of working on their thesis. So here is an outline. I'm going to start with a reduced rank regression, and for this I'm going to use the idea of matrix projections. And I will briefly outline what is a matrix projection, what kind of tools you need. Then I will put it in a high-dimensional context. You will know what exactly is a high-dimensional context I talk about, and n smaller than p, n bigger than p, etc. And then the second part of the talk is actually based on envelope methods. Envelope methods was introduced more recently, I think about 7 years ago by Cook. So I'm going to talk about envelopes, and I will use the concept of envelope-based sparse reduced rank regression method, once again applied to multivariate linear model, and then present some theoretical results and some simulational results. As you can see, there are two topics here. One may wonder why there are two topics, why you have two different methods, and why not you pick the superior one of the two. It will turn out that the goals or the underlying problem for the two techniques are different. The goals are different. So therefore, it is not reasonable to compare one with two because the goals are different. That's what I'm going to emphasize as I start presenting the technical details. So, first I'm going to talk about reduced rank regression, and reduced rank regression I'm going to specifically orient it towards a matrix projection for a high-dimensional data. First, let me give you the setup. I want to explain the introductory part of this and then introduce the methodology that we need. Some of you may have already seen some matrix projection in a linear algebra course. So this is a refinement of that. So let us start with a multivariate linear regression problem. We have n observations, and I'm going to say that we have r responses, and that is corresponding to y. That is my multivariate response matrix. And I have p predictors. The p predictors are represented by the matrix of predictors, which is my x. Then I have two quantities here. P is going to be a regression coefficient matrix, which is in the classical multivariate linear form, and it is of dimension p by r, because I have p is the number of matrix predictors and r is the number of responses. So my matrix B, which is my unknown matrix of parameters, is going to be of dimension p by r. Then I'm going to have an error, and the error matrix, only thing that I'm going to assume is that they are independent of each other and they are centered to have mean zero. Because if they are not mean zero, they can be adjusted with my matrix B and the design matrix X. But I'm going to allow the variances to be heterogeneous, sigma ij square. A simpler scenario will be the constant variance, but that's not of interest in the practical problem that we are looking at. Then, what I'm going to assume, this is something that Vijay already pointed out, is that you may have a data, you may have a dimension, but you may assume that it lives on a low rank structure. The low rank structure in this case is assumed on the coefficient matrix B. If you look at this, what you are saying is that this matrix B lives in a lower dimension, and that is what I am assuming here. So the rank that is represented by the rank of the matrix, I'm going to assume it to be D. But D, since I am assuming it is a low rank structure, obviously has to be smaller than a minimum of P and R. And P and R, as I have defined before, corresponds to the responses, the predictors, etc. Then we know from our decomposition theorems in linear algebra, the matrix B can be decomposed as AC, the product of two matrices. A will be a P by D matrix because D is the dimension of the matrix B, and C will be a D by R matrix. This is sometimes called as AC decomposition in linear algebra. That's the reason I have used A and C here. So the model in this particular case, the model that I presented earlier, is the multivariate linear regression model. In this case is called reduced rank regression model. What we essentially do is that by assuming this low rank structure of the coefficient matrix B, we are essentially, effectively, reducing the number of parameters to be estimated. In this model, without any constraint, the number of parameters will be P times R. By allowing the lower rank structure, we are essentially reducing the matrix, the number of parameters to be P plus R times D. Of course, when in the large dimensional data, big data context, large dimensional data, P plus R times D will be significantly smaller than P times R. So essentially, we will be improving the inference with regard to the precision, etc., if we are able to do this. And this is a reasonable assumption, in fact, in many multivariate regression problems. And what you can do is you can interpret that there are R responses, but the R responses are related to the P predictors, but not all the predictors are absolutely relevant. So we say that they are related only to D effective linear predictors. And that is the presumption, and that is why this assumption may be reasonable in many cases. Of course, the dimension or the magnitude of D is going to tell us how much of a reduction we have effectively achieved. And the data that I am going to give later, I will demonstrate this. Okay, so if some column vectors of a predictor matrix X are nearly linearly dependent, this is the multicollinearity that was mentioned in the previous talk. We know that in the case of multicollinearity, the performance of the reduced rank estimator would not be satisfactory when the predictor variables are highly correlated or in signal to noise ratio turns out to be small. And this is one of the drawbacks that's often pointed out, that so we have to take this into account when we come up with a methodology. So I'm going to first give you the main result, and some of these will resemble like lasso type techniques. This was also pointed out in many of the talks before. We will have an objective function. Since we are working with multivariate linear regression model, the objective function may be a quadratic form. But the quadratic form, we want to penalize in a certain way, and that is where the lasso type penalty will be brought in. And then we will look into estimation in this particular framework that I am talking about. So, in order to avoid this, I mentioned about the multicollinearity problem. So what I'm going to do is we propose 3 types of reduced rank estimators. And what we do is we introduce a nuclear norm penalty in a multivariate regression model, and we talk about a random projection or average random projection, or you can do principal component analysis. There are 3 different techniques, and I will talk about those 3 different techniques. So why I talk about the big dimension for high-dimensional data. The number of parameters P and R can be either less than the sample size n, or it may be greater than n. Greater than n is the classical setup. Less than n is the classical setup. Greater than n will be small n big P problem. And I also have to highlight again that I am not assuming anything about the variances of the error term. All I assume is that they have different variances, sigma ij square. So it is a heteroscedastic sort of error term that I am assuming for generality. So I'm going to talk about first estimation method. And I want to mimic some of the properties that inherently present in our least squares theory. So I want to come up with some estimation method. First one I develop is a two-step estimation method. For that, what I do is I take a low rank matrix which is of dimension D, for example, or K, and I'm going to assume that it is utilized to approximate the data matrix. And then next perform reduced rank regression with a penalty, as I mentioned before, and that is the second step. So for the first step, I have to first introduce a approximation method which is going to give us a lower rank matrix. And the low rank matrix approximation of X is the usual Q decomposition. I take X tilde. Please note that X is the original matrix, but I want to approximate it. So I put a X tilde. So X tilde is an approximation of X. Then the estimation method will rely on X tilde because it is of lower dimension. So X is pre-multiplied by QQ transpose. And I have to explain what exactly is the Q matrix. So I can have a pre-multiplier and a post-multiplier. For example, I have XS. If XS is equal to Q times R, what are Q and R? Q is a n by k matrix with k orthonormal columns. So that is the lower dimension and they are orthonormal. R is an upper triangular matrix with positive diagonal elements and it is a k by k matrix. If X times S is equal to Q times R, S is a random matrix. Then we have achieved an approximation for X as X tilde. So this matrix Q, which is of k orthonormal columns, gives us a way to approximate my matrix X by X tilde. Once I have this approximation, then I can introduce a reduced rank regression using a usual penalty method. And that will be my second step. So this is the two-step. So for a data matrix X, I'm going to first take SV decomposition. And SV decomposition is gamma lambda P transpose, and that will give the top k principal components xk can be extracted from X, and you can let X1 to be X times P1. And P1 denotes just the k right singular vectors of X. For the second low rank matrix approximation method, instead of basing it on QQ transpose X, I can base it on P1 transpose, which is another approximation. So there are two approximation methods that we can come up with based on the linear algebra results that we know. All I do here is something similar to a singular value decomposition. X1 I take as X times P1. P1 is the k right singular vectors of X. So for the second low rank matrix approximation now, I post multiply by P1 transpose, and that gives me another approximation. So these are two different approximations and they are not equivalent. So now, what is the estimation method that we need to introduce? Of course, since we are dealing with the least squares theory, we take the quadratic form y minus the approximation of x multiplied by b, and that I minimize. That is my objective function. But as mentioned earlier, we have to introduce a penalty. And the penalty that I introduce is a nuclear norm penalty. And that is simply x tilde b. Remember that x tilde b is an approximation of x multiplied by matrix of parameters and mu is a tuning parameter, just like we do in lasso. So this principle is very similar. As in lasso, we have where it is an absolute norm, here we are exactly using a nuclear norm penalty. In this particular case, what is nice is because of the approximation that I introduced here, QQ transpose X, which is my approximation of X, if I plug it in and I can actually optimize with respect to my parameter matrix B. And it turns out that it is possible an explicit estimator can be obtained. That is what is given here. So a minimizer of this objective function of quadratic form plus a nuclear norm penalty with a parameter mu. I have not mentioned how to select this tuning parameter. And this tuning parameter selection I will discuss when I come to a numerical data, for example. You can use cross-validation, which is one of the common techniques that is used. So let us take x tilde to be QQ transpose X, and then I have Px tilde Y has a singular value decomposition that I mentioned earlier, UdV transpose. Then the minimizer of 4, you go through a matrix derivatives calculations and you can explicitly solve, and that gives me the estimator B tilde. I use the B tilde because I am approximating the matrix X by X tilde. This D, the matrix D that appears here, is a diagonal matrix. And I also mentioned earlier that diagonal matrix should have non-negative elements. And so I take the elements lambda I P X transpose Y minus mu, and then I put maximum of that and 0, so that I have a non-negative condition satisfied. And this is an exact estimator. Of course, we want to know something about the magnitude of its bias, its predictive error, what about its asymptotic properties, etc. So you will notice that I am not giving any proofs anywhere because they are not so simple. So it is better to just highlight the result and explain why they are interesting or why they are useful. So first thing is, instead of, for example, using the first approximation, if I use the second approximation, which is based on the matrix P1, something similar to principal component analysis, then also if I have a singular value decomposition for Px tilde Y as U dV transpose D is the diagonal matrix, there also I can derive an exact estimator B tilde. So I have an exact form of the estimator, and we can do many things. One of the things that Vijay pointed out is if we twist the data, what impact each parameter has on the response variable, we will be able to do explicitly here. We can also evaluate the magnitude of the bias, the mean square error, because of the explicit form of the estimator. I have two different forms based on two different approximants for the matrix X. So I'm going to go to the next page. And one of the things I talked about is I have to know how to estimate the rank of the matrix B. And that is an important, remember that the matrix B in our case is the matrix of parameters. So we need to have an idea about what rank are we looking at. So the rank of the coefficient matrix B I denote by R0. It is nothing but the number of effective linear combinations of predictor variables that relate directly to response variables. The others are going to be irrelevant according to us. So in practice, these are unknown parameters. So we need to estimate the rank of B. And one method of rank of estimation B is given here. And once again, this is going to be based on, I look at these lambda i's that I introduced before. They are like principal component analysis coefficients. I pick the rank to be the maximum of I, where this coefficient is larger than a threshold value. But remember, this threshold value depends on the tuning parameter mu. And that's what I mentioned here. K represent the number of columns of random projection matrix S, and Rx is the rank of the predictor matrix X, and eta, your tuning parameter that we need to determine. And we can determine these by cross-validation. And I don't want to go into the details, but when I come to the real-life data, I will show you how it is implemented. So this is one way in which we can, given a data, we can come up with an estimation method for the rank of the matrix B, and then we work with reduced rank regression estimation. First thing is, whenever we come up with an estimation of the rank of the matrix, we need to establish some results with regard to its properties. How good is this method of estimation of the rank of matrix B? And that is what is stipulated here. So I am assuming making the same assumption about the error terms. They are heterogeneous. And then I have here the result, which says that if I estimate my rank of the matrix B by R tilde, I ask, what is the probability that R tilde is not equal to the true value of the rank, which is my R0? R0 is the true rank of the coefficient matrix B. So I ask, what is the difference between R tilde, my estimate, and the true rank R0? What is the probability my estimate is different from the true rank, and that goes to 0 as the number of observations plus R goes to infinity. So you can consider two different scenarios. A fixed n and R becomes large, or R increases with n and n becomes large. In both cases, this result tells you that you are estimating the true rank accurately. That's the first result that we need. Now that I have proved that I can estimate the true rank of the matrix B accurately, now I give you two results with regard to the estimates themselves. The first result corresponds to the bias. Expected value of xb minus x tilde b tilde. X tilde is the approximant of x, because I am not using the original x. I am using the approximant of x, and I am using the estimate of b, which is based on x tilde. I ask, what is the expected difference? And I can establish a bound. And I can show that this bound actually goes to 0 as the number of observations goes to infinity, essentially proving that I have asymptotic unbiasedness. This is not only for the first approximant. If I instead use the second approximant based on the PCA idea, orthogonal columns, once again, I can get an upper bound, and I can show that that upper bound actually goes to 0. Now, one of the things that we see here is, in order to show asymptotic unbiasedness, we are not relying on any of the known results, because the method used here is actually a different method for dimension reduction. So one way to prove asymptotic unbiasedness is to derive a uniform bound and then show that that bound actually goes to 0. And that's one way to prove the unbiasedness. So I'm going to present first some simulation results. And then I will give you illustrative data which explains the problem and also how the methodology works. By the way, there are umpteen estimators, reduced rank estimators that are available in the literature. I have here that proposed reduced rank estimators. I denote them by nuclear. They are nuclear norm penalized estimator. I explain the single random projection. I can also use average random projection. That means I average all the single random projections that I get an average random projection. And I can also use the approximates based on the principal component by constructing orthonormal columns. So those are three methods. And there are existing reduced rank estimators, what are called as rank penalized estimator. There is a robustified adaptive nuclear norm penalized estimator, etc. So there are three commonly used estimation methods for reduced rank estimation in the literature. So what I would like to do is to see how the proposed estimators perform in comparison to the estimators that are already in vogue. Now, one way of comparing them is what I call as a median rank estimate. The median rank estimate says that if I am going to observe how my estimation works, the median rank, so I estimate the ranks, and the estimation of rank says how much I can reduce the dimensionality. And what I want to know is every time I perform a simulation, I will come up with an estimate of the rank, and I want to report the median rank. If I seriously underestimate, my median will be a serious underestimate of the true rank or not. If I seriously overestimate often, the median will be larger than or not. So a median rank estimate seems to be a natural quantity based on which we can compare different methods. And the other thing that I can do is to talk about correct rank discovery percentage. A correct rank discovery percentage is another important criteria, and it's self-explanatory. What you want to know is how often you correctly recover the rank of the matrix. That's the second criteria. Here, I have presented three different scenarios. Unfortunately, I don't have time to go over the three different scenarios, but they are based on 100 simulation runs. Please note here that this is a high-dimensional data problem. I have n equal to 30, but p is equal to 40, and r is equal to 40. So I have a 40-dimensional matrix, 40 by 40 matrix, but actually the rank of the matrix is only 10. So that means out of the 40 regression variables that could be used for prediction, only 10 of them are most pertinent, the others are not pertinent. So I have introduced correlation row, which is 0.1, 0.5, 0.9, and I explained here that what is the median rank estimate and what is the correct rank recovery percentage that is described here. And what is important is to note how often these values are close to 10, because R naught is the actual rank that I have introduced in my simulation study. You can see that some of the methods produce my rank to be close to 10. However, that in the simulation scenario, different scenario, sometimes a serious underestimate can occur. And that is counteracted by the regression method that we introduced by reducing the dimensionality to begin with. So in this case, a reduced rank estimation method does work in your favor. That's one scenario. There is a second scenario where we introduce even a more serious sort of scenario where these methods actually estimate the R naught significantly low. and that is one of the complications that comes across in many different methods, that multicollinearity. If the situation is highly severe, you have this problem, which was pointed out by Vijay in the previous talk. Even there, the situation with regard to the reduced rank estimation based on projection method does not suffer at the same level, but still suffers from underestimation. And this is one of the things that I wanted to point out. Now we can also talk about the predictive error, mean square error, in terms of total mean square error for the whole matrix B. And you can compare the methods, and it turns out that in terms of predictive mean square error, the methods that are proposed are as good as the existing methods, if not better, in some of the scenarios. The first one is PM that I talked about. The second one is the mean square error, and there are three scenarios. These rows are created in order to introduce more spuriosity or more sparsity, depending on how you view it. Now I'm going to give you a real data. This is a data that is a DNA data. It is a breast cancer data set. It consists of 89 samples comprising gene expression measurements and comparative genomic measurements. And these data are available actually in the R package on PMA. Previous studies on this particular data set have demonstrated that certain types of cancer are characterized by abnormal DNA copy number changes. So therefore it might be of interest, of a practical interest, to identify the relationship between DNA copy numbers and RNA expression levels that are observed. So what is the data? We look at chromosome 18 that people have studied before. We have P, in this case is 294. That is the dimension for the P. And R turns out to be 51. And the N, in this case, is 89. These are the response variables. These are the number of predictors. The number of data points is 89. And you can see that N is significantly smaller than P. So first what you do is you center the matrix X and scale both the response matrix and Y matrix, response matrix Y and the predictor matrix X. Then we are ready to implement our method. But we have to check the prediction accuracy. The prediction accuracy we can evaluate based on predictive mean squared error. And the predictive mean squared error is going to be the observed value of YT minus what I had predicted based on XT times B hat. B hat is the estimator of B that I have determined from my reduced rank estimator with nuclear norm penalty. And I divide it by the number, NTR. And that is what we have to look at. NT is going to be based on how we divide the data. This is something that Vijay talked about. So the data is going to be split. And I have a training data set and a test set of size 19 and 70. Of course, you can do this average. For example, you can do a selection, and based on the selection of 70, you will have a test size of 19, and you can do average calculations for predictive mean square error. The training data set is used to achieve the estimation, and the tested data set is used to evaluate the predictive performance based on 18. And the tuning parameters, remember I mentioned about the tuning parameters. The tuning parameters are obtained by cross-validation. You can use a 5-fold or 10-fold cross-validation, which is what was implemented here. So here I have given the predictive comparisons based on the data split at random 100 times. So the data was split 100 times at random. And the rank is given here. What were the ranks that were estimated and what were the predictive mean square error? And I have given here the predictive mean square error for the three methods that are available in our package, which are the common methods, and these are the 3 predicted methods. And one of the things that we do observe is that this MSN method turns out to be slightly better than the other 2 methods that I talked about. So let us look at it in terms of a box plot, and that is a interesting sort of feature that it gives. For example, it shows you that the 3 methods that are proposed are not all same. They are not equivalent, but they have some relative merits depending on the data set that you are analyzing, etc. But in general, the MSN method that was introduced turns out to be better overall. And let me conclude here for the first part, saying that there are 3 methods introduced, one based on approximation tilde that I explained based on matrix Q. Second method I introduced is based on P matrix, and the third one is average projection method, which seems to be better in general. Now I'm going to introduce method of envelope. By the way, the method of envelope is rather new into the generalized linear model or multivariate linear model context. I think it has been known only for the last 8 years or so, or 7 years. So I'm going to first introduce the envelope itself. So once again, I start with the same multivariate linear regression model. Epsilon is an error vector. Now I allow general context of correlation. I don't need uncorrelatedness in my error term. Beta is a regression coefficient matrix. As before, it is of dimension R by P. X is a predictor vector. I have a multivariate linear regression model. Envelope method is an important development that is credited to Cook. Cook had several papers on the envelope method. It is another method to reduce the dimension of the response variable or the predictor variable. You notice the difference. I mentioned that I put forward 2 methods. The first method is suitable for reducing the dimension of the predictor variables. This method is particularly useful for reducing the dimension of the response variable, y. And the key point of the envelope method is to look for the following aspect. If you look at the mathematical formulation and try to understand what it is trying to achieve, what it does is, I have a correlation matrix in my error term. That is my sigma. That is my covariance matrix. And what it looks for is a subspace of sigma that will contain a span beta such that if I take Q based on the subspace psi of the projection of y given x, that will be independent of x. If I take the covariance between the projection of y based on the subspace q psi with the p psi y given x, it is going to be 0. So what does this mean? This means that the key idea of the envelope method is to split the matrix sigma into 2 subspaces. The subspace psi is going to give me the essential part that I need for making my prediction on the response variable, q psi y. But what it is left behind, that is my p psi y, is uncorrelated with the projection that I have made. So this is what is called as an envelope method. And I have not given the reference here, but if you do a Google search, you will find it is a Biometrica and JRSS Series B paper by Cook and his co-authors. So I'm going to start with my multivariate linear regression model, y equal to beta x plus epsilon. So the envelope-based reduced rank regression then will ask for a projection of y or a transformation of y, gamma transpose y. That will be equal to not b as we had bx, beta x before, but it will be some eta times bx, And this error, because of this transformation that I make, is going to change to gamma transpose epsilon. What is beta? You can immediately see that beta is going to be gamma times eta. Beta is going to become gamma times eta beta. That's what I'm going to get with respect to B. So I have a relationship. The transformation that I do gives me a relationship between the coefficient, and also it tells me what happens to my assumption on the error term. The error term no longer has a covariance matrix sigma, but it is going to have a covariance matrix gamma transpose sigma gamma. That's what we'll end up with. So this is related to a singular value decomposition that we know. You take eta b, and I can write it as UDV transpose. Sometimes people call it as UV transpose. So UV decomposition. So this is the singular value decomposition where U is going to be of dimension U by D, V is going to be of dimension P by D, but they are both D-dimensional matrices or D-rank matrices, and they will have orthogonal columns according to the singular value decomposition. And that is the critical part for my result. So, main result I'm going to give you quickly, then I can go to the simulation and data analysis. The first thing that we need is an objective function. The objective function is going to be very similar. I will have the quadratic norm, and I have to put a penalty term. I have P penalty terms, and you can give a weight function Wj, like for example we use in lasso, and that's what I mentioned. Lambda n times this is an adaptive group lasso penalty function because I attach a separate penalty for each one of those terms. So I need to minimize this objective function with this lasso penalty. And there are two things that we can prove, and this is what in dimension reduction technique called as oracle property. The oracle property has two properties. First one is called sparsity. What does the sparsity say? That I estimate my regression coefficients beta, which is in the complementary set, that is the space that I left behind, and they should be irrelevant. So that means my beta estimate for the complementary part that I left behind should be equal to 0. This probability goes to 1. This is what is called the sparsity property of the estimation. The second property is the asymptotic normality. If I look at the estimate in the subspace that I am interested in, that is the estimate which is the vector in the space A, that is my space that I am interested in, and the true vector of the regression coefficient in the same space, the difference multiplied by root n, this is the root n consistency, goes asymptotically to a standard normal distribution with a variance covariance matrix that can be consistently estimated. So I have asymptotic unbiasedness, I have sparsity, asymptotic normality, and I have consistency. And the oracle property of the estimation method thus follows. So this is another sort of a point. You can also allow P and R to vary, increasing with the sample size. For example, you can take n increases and the R, for example, the number of responses, or P, the number of predictor variables you have, grows with n. Even in that case, you will be able to prove that the estimate of the regression coefficients that I get outside the set A is not equal to 0. That inside the set A it goes to 1. Outside the set A it is equal to 0 goes to 1. And this is the sparsity property that we can prove. So I'm going to give you quickly a simulation result. Once again, my simulation result is going to base on two quantities. One is the predictive mean squared error. The other one is the average correct ratio between the number of correct selection and the total number of relevant variables. Remember that I can select the true number of variables, but I may select the wrong ones. So what I want to know is there are true significant response variables. Out of them, how many did I select? That is my average correct ratio, which measures the ability of selecting relevant variables. So there are different methods. OLS is the ordinary least squares estimator, and the estimator proposed by Cook et al. Is the standard envelope estimator. And then you can also do an envelope-based reduced rank regression estimator. So there are other estimators that are available in the literature based on lasso penalty, adaptive group lasso penalty, envelope-based sparse reduced rank regression estimator with group lasso, etc., etc. There are many, and I compare them here. And what I have compared here, it clearly shows that in the case that when n is much larger than p and r, the ordinary least squares estimator is not so bad, of course. But as the situation changes, then the ordinary least square estimator can run into some difficulty. And I have presented here the proposed estimation methods. And you can see that they are comparable to the methods that are already in existence with regard to the, and this is based on 50 simulations. And here I have chosen, for example, P and R to be larger, but it is much smaller than N. This is the classical scenario where I give the variable selection comparison. What is the true variable selection? One thing that you should look at. People usually look at the predictive comparison. The predictive comparison of 1.474 and 1.436 doesn't tell us the whole picture because it only says about how good are the estimates of the parameters. But you should ask how many times the true variables that are significant are being selected, and that is a completely different picture. According to this method, it selects the true significant variables 100% of the time. This method selects 67% of the time when P is equal to 30 and R is equal to 20. As P increases, some methods lose efficiency in terms of picking the correct variables. So there are two quantities that we should look at. But both these scenarios are favorable to statisticians where we have N larger than P. What happens when the situation is different? For example, here I have taken to be N equal to 60, but P equal to 70, number of responses equal to 70, but the dimension is equal to 5. And I show again, for example, what happens to the mean predictive comparison of the methods, and it turns out that the methods based on envelope based with lasso type group penalty works very well in addition to having the property. You can also ask, how often do you select the true variables? And you can see here that the SPLS method selects 83% of the time, but when N is much smaller than P, when P grows, the proportion of times it selects the true variables decreases significantly. And that happens to all the methods. But how much does it decrease depends on the method that you use. The proposed method still works very well compared to the existing methods. So I'm going to give one real life data that has been used in the literature before, and this is available once again in a R package called SPLS. The response matrix in this case is Y. It consists of 542 cell cycle regulated genes. The cell cycle was measured by taking RNA levels on genes at 18 time points using what is called as alpha factor arrest method. The description of this data is available in plenty of papers. So the matrix X corresponds to dimension of 542 by 106. That is the dimension of the matrix X. It contains the binding information of the target genes for a total of 106 transition factors. So I have 542 regulated genes, and for each I have 106 transition factors which are called TFs. That is the dimension of X. So in this case, we have number of individuals is 360. P is equal to 106. R is equal to 18 in the training data set. So we selected the number of factors D equal to 4 by a 5-fold cross-validation, and that is the D that is used in the proposed estimation method. So the dimension of the envelope U was selected by a 5-fold cross-validation, and that is my U value. This is my D value. So the matrix I'm going to come up with will be dimension U by D. So U is selected to be 6 by once again a 5-fold cross-validation, and this is the result I get. The top part of the table gives me prediction comparison based on data split at 100 times. You can of course make it 500 times. The time becomes essence. And you can see here that the proposed estimation methods has very similar predictive comparisons compared to the method that are available based on random forest, based on, for example, lasso penalty-like functions, reduced rank regression methods. I also talk about variable selection comparison based on data split at random 100 times. What are these MNSP and RNSP? These are the same quantities that I introduced before. This is the median number of selected predictors. So when I have 30 here, it says on an average, it selects the median is selected to be 30 number of predictors. The confidence interval or the range for the number of selected predictors goes from 19 to 53. But the SRR, which is the reduced rank regression estimates based on the usual lasso penalty, has 77 based on the method that is introduced by Cook et al. Turns out to be 77. The range turns out to be 45 to 89. The proposed methods come up with about 64. So from it looks like the variable selection is between the SPLS and the reduced rank estimation based on the methods that have been introduced before. So it turns out that the methods that are projected have reasonable properties. So I will stop here, and thanks for your attention.
Thanks, Professor Bala, for your interesting talk. I think your model is very useful because there is no restriction about the sample size, so it's a very good model. We don't have time for questions.
That is correct, but with one modification.
Yeah.
It can work with a high dimension where n is smaller than p, and it can work with low dimension when n is larger than p. But the performance of the method in terms of reducing the number of variables will be less efficient when n is much smaller than p, but it can still do the job. That's the important point. Yeah.
Thank you. Thank you for your talk. Now we're going to the next conference.
Thank you, Bala.
Thank
it was
you.
a pleasure to have you here.
Thank you. I enjoyed it. Thank you very much. Good luck, everyone.
Thank you.
Thank you.
Thank you.
Thank you.
Is it okay?
Yeah, I think.
Okay.
The next presentation, I don't know, Ulysses?
Yes,
I think you can present yourself because you're not going to present yourself. Are you okay?
I don't hear any sound. Is it a problem at my end or at your end?
I don't know.
I think it is here.
Oh, okay.
Yeah.
All right. Okay.
Ulises is going to present I suppose, a profile on Professor Barnard Nielsen.
Sí.
Okay.
Sí. Gracias. Nada más que tenía problemas con la pantalla. La presentación va a ser en español. Buenas tardes a todos. Mi nombre es Ulises Márquez y soy investigador de cátedra asignado a la Unidad Monterrey del CIMAT. Déjenles comparto mi presentación.
Para darles una idea en lo que entra la presentación, invitamos al profesor Barnard Nielsen porque ha sido una persona muy cercana a CIMAT desde años atrás. Incluso hasta se celebraba en CIMAT, Guanajuato, sus 70 años. Nada más que por las condiciones de la pandemia no puede salir de su casa y pues por esa razón nos pidió que hiciéramos esto, en particular a Ulises, porque Ulises estudió ahí en Aarhus, en Dinamarca, y lo tuvo como profesor, además de que ya lo conocía previamente, ¿no? Y la situación de la pandemia ahorita está muy, muy mal. Hoy en particular amaneció todavía peor la situación. Se va a volver a cerrar Dinamarca completamente porque ya se contagiaron ahora los minks y es otra cepa y no está contemplada en la vacuna. Así que no pudo tomar decisión mejor el doctor Barnard Nielsen porque él tenía que ir a la universidad para poder usar los equipos. No tenía suficiente equipo para la transmisión en su casa y por eso pidió esta situación. Y bueno, creo que no se equivocó en nada. Bueno, no son buenas noticias para el mundo, menos para Dinamarca, ¿no? Adelante, Ulises.
Sí se ve ya mi presentación, ¿verdad?
Sí.
Ok. Bueno, como les comentaba Chela, a lo mejor algunos de ustedes se preguntan por qué vamos a presentar un libro en esta celebración de los primeros 40 años del CIMAT. Como Chela les estaba comentando, cuando a principios de año ella y yo planteamos este evento, una de las primeras personas a las que consideramos invitar fue precisamente a Ule. Y cuando lo invitamos, le solicitamos que su plática fuese sobre su perspectiva del futuro de la probabilidad y la estadística, como una forma de motivar a los estudiantes y a los investigadores jóvenes a que se adentraran a esta área, ¿no? Eso fue antes de que la pandemia cobrara fuerza, fue por ahí de finales de enero, principios de febrero, y en ese momento Ule aceptó la invitación. Pero pues un mes más tarde, con el desarrollo de la pandemia, tuvimos que cambiar la fecha de la celebración del evento, la tuvimos que posponer. Originalmente estaba planteada para el 6 y 7 de septiembre y pues al final pues la terminamos haciendo en estos días, ¿no? Entonces, pues en el correo en el que declina su participación, él dice, bueno, no puedo dar la plática, pero puedo enviar unas copias de mis memorias académicas para que los estudiantes las revisen. Y esta idea a Chela y a mí nos agradó mucho, ¿no? Porque al final de cuentas lo que queríamos con su plática era que pues sirviera de motivación a las futuras generaciones de estadísticos y probabilistas. Entonces, mediante esta forma, Ule lo que está proponiendo es que pues esa motivación salga de su experiencia personal como investigador, la cual está plasmada en el libro, ¿no? El libro que lleva el título que está ahí, Stochastics in Science, Some Autobiographical Notes, contiene las memorias de la carrera académica de Ule y contiene muchos detalles. Hay una copia del libro en CIMAT, Guanajuato, la cual fue traída por Steve Torbensen cuando visitó a Víctor Pérez Abreu, creo que hace un año y medio. Y Ule quedó de enviarnos algunas copias acá a CIMAT Monterrey, ¿no? Entonces, pues para aquellos que son nuestros estudiantes en CIMAT Monterrey y aquellas personas que nos siguen de CIMAT Guanajuato, pues pueden encontrar una copia del libro para revisarla, ¿no? Entonces esa fue la primera razón por la que decidimos hacer esta presentación, pues para honrar que Ule estaba interesado en la participación y pues para motivar, ¿no? La segunda, pues es que, como Chela lo mencionaba, Ule ha sido un colaborador de CIMAT, particularmente ha entablado una buena amistad y colaboración con Víctor Pérez Abreu. Para quien no sepan, Víctor era investigador de CIMAT hasta hace un año, cuando se retiró. Y fue, bueno, la persona que introdujo a Ule al CIMAT. Y bueno, esta es la copia del libro, la cual pueden entender, la cual pueden consultar. Lo pueden comprar, pero tienen que pedirlo de Dinamarca. Hay una librería que lo ofrece, no sé si bajo qué condiciones, pero bueno, en las bibliotecas de CIMAT está. Bueno, cuando estaba preparando la presentación de este libro, me di cuenta que era la primera vez que presentaba un libro de esta naturaleza. Entonces al principio no me era muy claro qué era lo que tenía yo que hablar para poder pues presentar este libro para presentar los elementos de este libro, ¿no? Entonces, al final de cuentas decidí que les voy a hablar un poco sobre la vida académica de Ule, pues sin dar muchos spoilers, o sea, no pretendo que esta revisión sea una revisión completa. Hay muchos elementos en el libro que no voy a mencionar y es posible que algunos de los elementos que mencione no los recuerde con el detalle con el que viene en el libro, ¿no? Les sugiero que para tener los detalles explicados de forma correcta y detallada, pues consulten el libro, ¿no? Bueno, ¿quién es Ule? ¿Quién es Ule Vanders Nielsen? Para aquellos que no los conocen, Ule es un destacado estadístico y probabilista danés que tiene contribuciones en estadística matemática, en procesos estocásticos, en particular en la teoría de Levi. Ha propuesto varias distribuciones y muchas otras, ¿no? En esta presentación pues no voy a hablar de todas porque son numerosas, el tiempo no me daría para hablar de ellas. Y para ser sincero, conozco varias de ellas, pero no todas de ellas, ¿no? Sus contribuciones son muy numerosas y en distintos campos que pues no necesariamente creo que yo sea la persona adecuada para hablar de todas ellas, ¿no? Ule nació el 18 de marzo de 1935 en Copenhague. Fue bautizado con el nombre de Ule Elier Nielsen, pero cuando entró a la escuela se dieron cuenta que había otros 5 niños que compartían el nombre Ule Nielsen, por lo que sus papás decidieron pues cambiar el nombre y anteponerle a su apellido el apellido Bandorf, que era el apellido de soltera de su mamá. Entonces pues de ahí viene su nombre. Él tiene un grado doctor por la Universidad de Copenhague, aunque realmente su tesis la hizo en la Universidad de Aarhus, como voy a explicar un poquito después. La mayoría de su vida académica la pasó en la Universidad de Aarhus, que Aarhus es la segunda ciudad más grande de Dinamarca y pues es la casa de esta universidad. Pero también trabajó en la Universidad de Copenhague, pasó un año en Stanford, un año en Minnesota. También fue profesor visitante en Cambridge y es un profesor asociado en la Universidad Técnica de Múnich. Entre las distinciones que tiene, pues recibió el premio Humboldt de investigación del gobierno alemán en el 2001 que es un premio que se otorga a investigadores que creo que no están asentados en Dinamarca para que sigan, perdón, en Alemania para que sigan generando contribuciones, y además recibió un premio de la Universidad de Aarhus de investigación en el 2010. Además tiene 2 doctorados honoris causa. El primero es por la Universidad Paul Sabatier en Toulouse, el cual recibió en el 93, y tiene otro por la Universidad Católica de Leuven, el cual recibió en el 1999. En el libro se explica con detalle pues cómo fue su interacción con la Universidad de Toulouse, cómo empezó a colaborar con gente que estaba basada ahí, y pues lo que desembocó en que recibiera este doctorado honoris causa. Lo mismo para la Universidad Católica de Leuven. Algo que me llamó mucho la atención es el inicio de la carrera científica de Ule, ¿no? Él no empezó como estudiante de matemáticas, él empezó estudiando medicina y hizo una estancia para estudiar aspectos de bioestadística en el Instituto Centro, cual se encuentra en Copenhague. Bueno, realmente no sé si sigue ahí, pero estaba en Copenhague. Y trabajó bajo la tutela de George Rasch y Michael Weiss Benson. Realmente no sé si los estoy pronunciando bien, entonces ahí una disculpa si mi pronunciación no es la adecuada. El primero de ellos es conocido como uno de los padres de la respuesta al ítem, y lo que se conoce como la inferencia objetiva. El segundo hizo contribuciones en matemáticas actuariales. Y a lo largo del libro, Ule describe que considera a estas 2 personas como sus mentores. También cuenta que, pues, poco a poco ellos 2 lo fueron introduciendo a las discusiones sobre los problemas científicos que estaban atacando en ese instituto. Primero de forma informal, pero pues que fue algo que contribuyó mucho a su interés en la probabilidad estadística y en su formación como científico. Posteriormente, bueno, trabajando allí en ese instituto de bioestadística, tuvo la oportunidad de colaborar con Ule Malloy y Niels K. Herne, el primero biólogo molecular, el segundo un inmunólogo danés que obtuvo el premio Nobel en el 84. Cuenta que en ese momento lo que estas personas estaban interesadas en determinar pues eran algunas de las leyes fundamentales de la biología. En particular estaban estudiando la forma en la que se reproducen los bacteriófagos en células huésped. Ule colaboró en la solución de este trabajo y su propuesta fue resolverlo mediante un proceso de nacimiento y muerte. Eso da lugar a su primer artículo científico, creo que es su primer artículo científico en el cual plantea estos modelos y la solución que había encontrado el problema, ¿no? Creo que esa también fue su tesis. Entonces, motivado por su estancia en este instituto y la recomendación de sus 2 mentores, de George y Michael Weiss, decide estudiar probabilidad estadística, ¿no? De hecho, en el libro él menciona específicamente que sus 2 mentores le dijeron que el área de probabilidad y el área de estadística eran áreas en las cuales ellos veían un futuro. Por lo que se muestra en el libro, Ule parece que ya iba en esa dirección, pero pues recibir ese consejo como que lo animó más a continuar esta línea, ¿no? Entonces, pues decidió seguir su formación en esto, pero se dio cuenta de que no había cursos formales de probabilidad estadística en Copenhague y en general en toda Dinamarca, ¿no? Entonces, lo que hizo fue hablar con sus 2 mentores y con otros profesores que estaban en la Universidad de Copenhague, y lo que hicieron fue sugerirle una lista de lecturas que podrían ayudarlo en su formación. Él menciona que pues la lista fue demasiado grande, incluso a modo de broma dice que pues podría ser material para toda una vida, entonces tuvo de una u otra forma que acotar la cantidad de contenido que tenía que estudiar. Y bueno, también menciona que en su formación uno de los libros que fue muy importante por la forma en la que presentaba los problemas de probabilidad, sin mucha generalidad, pero con los suficientes elementos matemáticos de formalidad para que pues fue una exposición formal, pero a su vez una exposición que permitiera entender la intuición detrás de los problemas. Fue el primer libro de Feller, ¿no? También menciona, o sea, para aquellos que sepan, pues el libro de Feller está dividido en dos volúmenes, ¿no? El primer volumen y el segundo volumen. Él menciona que cuando él era estudiante, pues solamente se había publicado el primero de los libros. Bueno, entonces en ese sentido, Ule pues fue autodidacta porque no tuvo pues una formación asistiendo a cursos, ¿no? Posteriormente, bueno, él estaba basado en la Universidad de Copenhague. Como en aquella época era la Guerra Fría y cuando pues, era investigador en la Universidad de Copenhague, bueno, profesor en la Universidad de Copenhague, los rusos habían lanzado el primer satélite, el Sputnik. Bueno, los Estados Unidos respondieron dando apoyo financiero a múltiples proyectos a lo largo del mundo occidental. En particular, un profesor que estaba basado en la Universidad de Aarhus obtuvo un proyecto de la Fuerza Aérea estadounidense y este profesor lo empezó a invitar continuamente para colaborar, por lo cual pues ahí se da su primera relación con la Universidad de Aarhus. Posteriormente le ofrece una posición de profesor asistente ahí en Aarhus, teniendo solamente el grado de maestría. Entonces, cuando está en Aarhus empieza a desarrollar su trabajo doctoral, el cual pues es en familias exponenciales y condicionamiento, el cual pues trata sobre todo extensiones del concepto de estimador suficiente y de ancilaridad. Él menciona que pues algunas de las herramientas matemáticas que usó fue análisis convexo, y además, a pesar de que su tesis la hizo en la Universidad de Aarhus, considerando que no había alguien que trabajara en esta área, decidió someterla en la Universidad de Aarhus, decidió someterla a la Universidad de Copenhague. Cuenta que su defensa duró 6 horas y bueno, al final obtuvo el grado, ¿no? A lo largo del libro también se mencionan muchas de las relaciones científicas que Ule estableció, en particular con David Cox. Él menciona que pues había conocido los trabajos de David Cox y en una visita que tuvo a Londres, pues aprovechó la oportunidad de pasar a visitarlo. No lo conocía. Dice que llegó al Imperial College, en donde estaba basado David Cox, habló con la secretaria y le preguntó si podía tener compartir algunas palabras con David Cox. Para su buena fortuna, David Cox aceptó y pues de ahí inició una fructífera colaboración científica, ¿no? De hecho, el libro contiene una carta que le envió David Cox mencionándole el evento y menciona que había otro profesor ahí. David Cox no recuerda quién fue, pero parece que fue Preben Blasit, que es profesor en la Universidad de Aarhus. Pero pues también menciona que Ule se la pasó hablando todo el tiempo y que muchas de las referencias que Cox le estaba mencionando, Ule ya las había recibido, ¿no? Y bueno, esta relación científica y de amistad se vio fortalecido porque tanto Cox como Ule, ambos son amantes de la ópera, en particular de las obras de Wagner. Bueno, nada más mencionar que la tesis de Ule al final fue publicada como un libro gracias a la invitación de Kendall. El libro que aparece en azul es una edición reciente de su tesis que se llama Information and Exponential Families in Statistical Theory. Y el otro pues son uno de los libros que publicó con David Cox en Inferencia y Asymptotics, el cual se considera un libro muy influyente en el área, ¿no? Bueno, como empecé un poquito tarde, voy a tomarme algunos minutos más, ¿no? Bueno, nada, para mencionar algunos de los resultados por los cuales Ule es reconocido internacionalmente, pues voy a mencionar dos que fueron algunos de sus primeros resultados importantes, ¿no? La primera es la llamada P estrella fórmula, que ahora se conoce como la fórmula de Van der Nielsen, y que a sugerencia de David Cox también fue llamada la The Magic Mystery Formula. Este es una aproximación de la distribución del estimador de máxima verosimilitud. Aquellos que sepan un poco de máxima verosimilitud recordarán que asintóticamente se puede aproximar la distribución de este estimador utilizando el teorema del límite central, pero en algunos casos esa aproximación no es tan buena. Entonces lo que hizo Ule fue utilizar técnicas de geometría diferencial para proponer otra aproximación, y a lo final que llegó fue esta fórmula que aparece aquí, ¿no? En este caso, la C es una constante, la J es la matriz de información de Fisher, evaluada en el estimador de máxima verosimilitud, por eso el gorrito. E, pues es la función exponencial. L es la log-verosimilitud, evaluada en el estimador verdadero, o en el parámetro verdadero. Y la L gorrito es la log-verosimilitud evaluada en el estimador de máxima verosimilitud. Esta fórmula es muy celebrada porque, a pesar de ser una aproximación, en muchos casos, en particular en el caso de la familia exponencial, aproxima de manera exacta la distribución del estimador de máxima verosimilitud. Es algo que no se esperaba y se ha repetido en otras distribuciones. En sus memorias, Wille comenta que este problema, o el por qué esto parece suceder, se entiende un poco mejor, pero que aún hay elementos que no se entienden, ¿no? Y bueno, estas fueron algunas contribuciones a Sample Point Approximation y en desviaciones grandes, ¿no? Otro de los resultados por los que es muy conocido es por la distribución hiperbólica, la cual él propuso, ¿no? Él menciona que un profesor de la Universidad Técnica de Dinamarca, el nombre que aparece aquí es Jens Müller, estaba estudiando el tamaño de los granos de arena. Entonces, básicamente lo que hacen, pasan cribas hechas con redes y van separando los granos de arena en distintos tamaños, ¿no? Y cada vez lo hacen más fina para, pues, tener cosas más pequeñas. Luego asumen que el grano de arena es esférico, lo pesan y, pues, teniendo el peso, suponen que tiene una buena aproximación del tamaño del grano de arena. En ese entonces, la distribución que suponía que estos granos de arena debían seguir era una distribución gaussiana. Pero lo que vio este profesor, y seguramente muchos otros, es que al graficarlo en la log escala, no obtenía una forma parabólica, que era lo que se debería obtener si se está haciendo algo con una gaussiana. Obtiene algo que parece una hipérbola, y de ahí, pues, el nombre de distribución hiperbólica, ¿no? Viendo el problema, Wille se le ocurre cómo encontrar una expresión para esta distribución, y es la fórmula que tenemos aquí. Primero la encontró en la forma univariada, pero esta es la fórmula multivariada, ¿no? Y esta distribución tiene muchas aplicaciones. Por ejemplo, en aeronáutica se utiliza para analizar el despegue y aterrizaje de aviones. Tiene una aplicación un poco inesperada en relatividad. Si uno considera el momento de partículas en un baño María, si consideramos las restricciones de la relatividad, que nada puede viajar más rápido que la velocidad de la luz, pues da como resultado que el momento debe seguir una distribución que se conoce como la distribución de Jotner. Y esta distribución de Jotner es un caso particular de la distribución hiperbólica. Es una cosa que me parece muy sorprendente. Y bueno, no voy a tener mucho tiempo para extenderme un poco más sobre esto, pero este resultado, pues, le dio colaboraciones muy importantes, en particular con Ralph Becknott, quien es, o mejor dicho, era un militar británico que estudió las dunas de arena del desierto libio. De hecho, también es un geólogo y militar británico. Y de hecho hay un grupo militar, bueno, estuvo en Egipto durante la Primera Guerra Mundial, después regresa a Inglaterra, y al estallar la Segunda Guerra Mundial lo envían a la India. Después de la India lo vuelven a mandar a Egipto, y ahí sugiere a uno de los comandantes encargados de ese frente que podían utilizar el conocimiento que había adquirido estudiando estas dunas para plantear ataques más elaborados en las tropas enemigas, ¿no? Entonces hay un grupo que le llaman el Long Range Desert Group, y de hecho hay libros sobre este grupo. Y bueno, él empezó a colaborar con esta persona que tenía resultados que eran resultados empíricos. Cuando lo contacta Wille, pues menciona que esta persona, a Beck, no le dio mucho gusto que alguien recuperara sus resultados empíricos y que hubiera podido generalizarlos a algo que pues no era empírico, ¿no? Que establecer una teoría detrás de ella, ¿no? Bueno, así de manera general, estas fueron como todas las contribuciones que hicieron a Wille, un investigador reconocido, pero no son las únicas, tiene muchas, ¿no? Ha trabajado en leyes de probabilidad y divisibilidad infinita. En particular, generalizó la distribución hiperbólica a lo que se conoce como la distribución hiperbólica generalizada, y a un caso particular que se conoce como la normal inversa gaussiana. Estas son distribuciones en las cuales se puede suponer que se tiene una distribución con un parámetro aleatorio, una media y una varianza aleatoria, y pues estas dos clases de distribuciones son distribuciones infinitamente divisibles, que son una clase de distribuciones que tiene muchas aplicaciones y son importantes en las aplicaciones. También tiene varias contribuciones en procesos de Levy, en particular en teoría de Levy. Una de las cosas por las que es muy reconocido es por su propuesta del proceso Austin-Uhlenbeck. El Austin-Uhlenbeck es un proceso estocástico positivo que es muy simple, pero sirve para moderar, entre otras cosas, la volatilidad estocástica. El Austin-Uhlenbeck tiene el problema de que no guarda las dependencias a lo largo del tiempo. Entonces, esta propuesta de Euler permite introducir esas dependencias de largo alcance, ¿no? Una cosa en la que trabajó que me llama mucho la atención es que utilizando procesos de Levy, se dieron cuenta de que podían entender el enfriamiento de átomos por medio de láseres, ¿no? Entonces él trabajó un poco en esta dirección y logró establecer cómo se daba este enfriamiento y cotas del movimiento de las partículas, ¿no? Eso me parece una cosa muy impresionante porque pues no es el área de Euler. También tiene contribuciones en divisibilidad infinita, estadística cuántica. Esto también es muy interesante. De la mecánica cuántica, la física cuántica establece nuevos paradigmas, y esos paradigmas se pueden traducir en nuevas condiciones dentro de la estadística clásica, ¿no? Entonces, una de las cosas que estudió Euler es cómo esos paradigmas afectan los conceptos de suficiencia, ancillaridad y las familias exponenciales, ¿no? Ahí tiene varias contribuciones. También fue un pionero del uso de las técnicas de geometría diferencial en inferencia y en estadística. Ha colaborado en temas turbulencia, en particular con Jürgen Schmigel, quien fue mi asesor en doctorado en Dinamarca. Con él se han dado cuenta que los incrementos del campo de velocidad turbulentos pueden ser bien descritas por una de las leyes que Euler propuso, que es la normal inversa gaussiana. Y pues esto dio lugar, esta colaboración dio lugar a lo que se conoce como ambient stochastics, que ha sido pues el tema de investigación de los últimos años de Euler. También ha trabajado en temas de econometría, en particular propuso un modelo que es muy usado, que se llama el modelo BNS, el cual propuso conjunto con Neil Shepard, que creo que ahorita está en Harvard. Bueno, podría extenderme más sobre esto, ¿no? Bueno, nada más mencionando la relación que tiene Euler con el CIMAT. La primera vez que visitó el CIMAT fue en 1993 para el Workshop on Biostatistics and Statistical Inference. Él menciona en el libro que fue invitado por David Sprott y por alguien que en ese momento no conocía. Y ese alguien es Víctor Pérez Abreu, que como les comenté, era investigador de CIMAT y de hecho fue director del CIMAT. Y ahí menciona cómo su relación con Víctor evolucionó para colaborar y en amistad. Esa fue su primera visita a CIMAT. Luego, como Chela lo mencionó, en el 2006 se celebraron sus 71 años con una conferencia, esta conferencia en Stochastics in Science, de la cual pues estuvo centrada en algunos de los temas que Euler desarrolló a lo largo de su carrera científica y que tuvo pues muy importantes expositores como Albert Shirayev, Jean Jacot, entre otros, ¿no? Y bueno, la otra relación que Euler tiene es que pues, nos recibió a Orimar Sauri, que será uno de los expositores del día de mañana, y a mí, como estudiantes de doctorado de la Universidad de Aarhus. Y algo que se me olvidó, Euler también tiene colaboraciones con Octavio Arismendi y Carlos Vargas, que están en Guanajuato, encima de Guanajuato, ¿no? Y es una fotografía, si no me equivoco, bueno, en el año 2000 también se hizo el Congreso Internacional de la Sociedad Bernoulli, en el cual Euler participó. Creo que este fue del evento de sus 70 años. Y bueno, y para concluir, otra de las actividades que desarrolló y que son muy importantes y que se mencionan en el libro es que fue presidente de la Sociedad Bernoulli. La Sociedad Bernoulli, como algunos de ustedes saben, es la sociedad de probabilidad estadística más importante en el mundo, y además fue creador, bueno, fue uno de los creadores de esta sociedad y aparte del journal de la sociedad, ¿no? En la derecha tenemos un libro que es un libro que contiene la genealogía de la familia Bernoulli, que fue regalado a la sociedad por la familia Bernoulli, y en el cual la tradición es que cada uno de los nuevos presidentes la va firmando, ¿no? Aquí, de hecho, en el 93-95, Ule fue el presidente, y ahí podemos ver su firma. Y bueno, Víctor Pérez Abreu también fue presidente de la Sociedad Bernoulli, y de hecho podemos ver aquí su firma en el periodo 2009 y 2011, ¿no? Entonces, bueno, nada más para concluir. A grandes rasgos, pues el libro presenta las relaciones científicas que Ule desarrolló a lo largo de su carrera científica. Menciona muchas de las personalidades con las que colaboró y algunas de las cuales tuvieron impacto en su trabajo. Por ejemplo, menciona a Harald Kramer, que es el matemático sueco de la J de Kramer-Rao. Menciona a Mark Kac, un matemático polaco. Menciona a Kiyoshi Ito, a quien él invitó a pasar una larga estadía en Novus. Menciona a David Cox, a Ralph Becknold y muchos otros, ¿no? En el libro aparece, ¿no? Algo que me pareció muy interesante del libro es que responde de una forma amena una pregunta fundamental, que es ¿qué hace un científico? ¿Qué investiga un estadístico? ¿Qué investiga un probabilista, no? Y creo que esas preguntas quedan resueltas desde la perspectiva personal de Ule, y además muestra que muchos problemas del mundo real dan lugar a modelos o conceptos matemáticos muy bonitos, y que también se puede al revés, ¿no? Que hay conceptos matemáticos que pueden aplicarse con mucha naturalidad para resolver problemas que surgen en el mundo real, ¿no? Un mensaje que queda implícito en el libro es que la ciencia en sí es una actividad social, ¿no? Ule, da cuenta de todas las relaciones académicas que estableció, y queda claro cómo cada una de ellas influyeron en su investigación y en la forma en la que interpretó el rol de la probabilidad y la estadística, ¿no? Y para concluir, otra cosa que me gustó mucho del libro es que de forma lateral se da cuenta del desarrollo que tuvo la probabilidad de la estadística a lo largo del siglo XX y principios de este año, ¿no? Si bien es una visión en la cual se enfoca en los intereses de Ule, da una perspectiva muy interesante de cómo se desarrolló esta área y algunos de los debates que surgieron en ella, ¿no? Ya me extendí, creo que más de lo que teníamos planeado. Entonces,
fíjate,
yo creo que...
solo antes de que termines, noten, en 1983 David Cox fue el presidente de la Bernoulli, y el siguiente presidente, por respeto, deja en blanco la firma abajo y la hace a un lado.
Sí. Sí.
Como dicen, hay jerarquías.
Sí. Y bueno, nada más así como comentario, aquí está, por ejemplo, al final la firma de Edward Weimers, quien también ha estado en CIMAT. Pues Víctor, el investigador de CIMAT. Ahí está Jean Jacot, que también ha estado en CIMAT. No ha estado tanto tiempo.
Peter Hall también ha estado en CIMAT.
Ok. Entonces ahí nos damos cuenta de que pues el CIMAT, del rol que CIMAT ha jugado en el papel internacional que ha desarrollado a lo largo de su corta historia, ¿no?
Y creo que es justo también dentro de esta historia reconocer el gran papel que desarrolló Víctor Pérez Abreu durante todos los años que le dedicó a CIMAT, desde que terminó su doctorado en Chapel Hill y hasta recientemente que decidió jubilarse, ¿no? Pero dejó un trabajo no solamente en lo académico, en promover con los jóvenes, emocionar a los estudiantes desde la licenciatura, el de preparar muy buenos doctorantes, que todos son realmente, están muy, muy bien acomodados en el SNI o en lugares internacionales, etcétera. Y creo que merece también que lo nombremos en forma particular y especial en esta celebración de los 40 años de CIMAT, porque creo que fue una de las columnas y pues yo creo que todavía no encontramos sustitutos. Ojalá pronto lo tengamos. Bueno, yo con eso les doy las gracias a todos por esta sesión que era, pues digamos, los amigos grandes de CIMAT, y lo que no porque los otros no sean grandes, sino porque se lo digo por edad. Mañana, recuerden, tendremos la sesión desde las 9 hasta la tarde de gente que ha participado con CIMAT en diferentes escenarios y que quieren contribuir de alguna forma a esta celebración. Entonces los esperamos porque ellos van a traer muchas líneas nuevas, importantes, que están siendo demandadas y están trabajando en estos momentos en el mundo.
Sí. Y bueno, nada más recordarles que el libro va a estar ahí disponible dentro de poco en la unidad y hay una en el CIMAT, entonces los invito a que pues lean el libro y de primera mano